Okay, so now we get into the most complicated case, but we will limit how difficult this will be. So we're still working with the form, the integral of sine to the m of x times cosine to the n of x dx. But now we're going to have both exponents be even. Okay, so that's an and statement. Both of them must be even at the same time. And this presents difficulties. All right, now we're going to make our life not too difficult by making sure that when we add the exponents up, the total degree does not exceed 4. It starts to just become tedious if it's bigger than that, and we'll show you other ways to handle it when it gets to be a very long problem. Okay, so first of all, I want to show you what you shouldn't do with this problem. If you try to do this like a level 2, okay, it will fail. All right, and let me show you why. So we might be tempted to rewrite this as leave the sine alone and then rewrite cosine as cosine squared as cosine of x times cosine of x, because we, in order to do substitution, we either need a single factor of cosine or a single factor of sine. So we might think that would work, all right? The problem is we can't use the identity we used in level 2, which was that cosine squared of, we basically worked with the Pythagorean identity, sine squared x plus cosine squared of x equals 1, because we don't have a cosine squared or a cosine to the 4th or 6th. We don't have an even power. So the Pythagorean identity doesn't get us anywhere, all right? So I'll just put a big X next to that. This fails, okay? Cannot use. Maybe don't put an X, that makes it look like another variable. Say that we cannot use this, all right? And if we had written it the other way, if we'd broken up the sine into sine of x times sine of x cosine squared of x dx, same thing would have happened. You might think it's a good thing that we have a sine by itself for doing substitution, but we would come down to we can't rewrite the other factor of sine using the Pythagorean identity. So using the Pythagorean identity will just not help us here. So that doesn't work. So we need another trick, okay? The other trick is the following. You may remember from pre-calculus that there was a double angle formula, which then led to a half angle formula, but let's use the double angle formula version of this. And here it was. It looks almost like the Pythagorean identity, but it's not quite the Pythagorean identity because there's a minus sign in there. All right. So if there was cosine squared of x plus sine squared of x, it would be 1. But when you're taking the difference, it's the cosine of 2x. Well, now we can use the Pythagorean identity and we can go one of two ways. So way one would be that I could say that the cosine of 2x is equal to cosine squared of x minus, and then parenthetically, 1 minus cosine squared of x, right? So we've used the Pythagorean identity in order to rewrite sine squared. You can see, just doing a little bit of algebra, this will equal, notice it's minus negative cosine squared, so it's 2 cosine squared of x minus 1. All right, and then if I make another step, I can say that I'm going to write the 1 first. You'll see why later, just for an issue of symmetry. 1 plus cosine 2x, so I add 1 to both sides, is 2 cosine squared of x. Therefore, here's the big final step. Cosine squared of x can be rewritten as 1 plus cosine of the double angle over 2. So that's important. So I could take a cosine squared and rewrite it, okay, this way. We're going to see good things can happen, right? The other way I could have gone, I could do exactly the same thing. I'm going to go a little more quickly this time. I could have rewritten the cosine as Okay, therefore the cosine of 2x would be 1 minus 2 sine squared of x. Let's switch some sides. Bring that over to the right by adding 2 sine squared of x to both sides and subtract cosine of 2x from both sides. And now you can see, sine squared of x could be rewritten almost the same way as cosine squared, but it's 1 minus the cosine of 2x all over 2. So these two formulas will let me convert the even powers into odd powers. Notice we have a cosine of 2x to the first in both cases, but we do have a more complicated argument. Whoops, instead of having, get my screen back up here, instead of having it's cosine of 2x to the first power instead of a cosine squared of x that's in there. So we'll get a little bit more, it'll be a little more to handle. So let's rewrite the problem we had been working on. So we're still back on this example, the sine squared of x times cosine squared of x with respect to x. We can now rewrite that as the integral of 1 minus cosine of 2x over 2 times 1 plus cosine of 2x over 2, all integrated with respect to x. All right, now this becomes easier. So we've used our trig identities to rewrite this. One thing that's very nice to do is you have 2 factors of 2 in the denominator, bring those out so we don't have to worry about fractions. And then you have a product of a minus b times a plus b. So we should get, when we FOIL that, we should get the difference of squares. Okay, so that becomes cosine squared of 2x integrated with respect to x. All right, and so then we can rewrite this as 1/4 the integral of 1 dx minus 1/4 the integral of cosine squared of 2x dx, right? So you'll notice we just dropped this thing by degree 2. So we had started with sine squared times cosine squared, so that's degree 4. We're now down to a degree of 2. Okay, the first integral will be trivial, and the second integral is degree 2. So let's work with cosine squared 2x, all right? We can use our identity again for the cosine of x, and we could say that cosine squared of 2x, now remember the angle is 2x, would be 1 plus cosine of 4x, because we have to double the 2x, we have to double the angle, all over 2, right? So that means I can rewrite the entire expression as 1/4 the integral of dx minus 1/4 the integral of, let me bring that factor of 2 out, so I'll make that a 1/8 the integral of 1 plus cosine of 4x, all with respect to x. Let's break that into a couple of integrals. Let's just go ahead and call this 1/4 of x minus 1/8. We'll have the integral of dx minus 1/8 the integral of cosine of 4x dx. Okay, so let's keep going with this. So I have 1/4 x. Clearly this is minus 1/8 x, or hopefully that's clear. So when you integrate dx, you just get x. That's really 1 dx. And then we have to figure out how to integrate this. Well, this is a quick chain. Notice we have a 4x here, so we better get 1/4 of what the antiderivative of would be. So we end up with minus 1/32. The antiderivative of a cosine is a sine of 4x. So quick chain, because the antiderivative is sine of 4x, and we're integrating, we need an extra factor of 1/4 in front of that to make it work. And we tack on our plus c, all right? And clearly this simplifies. 1/4 x minus 1/8 x is 1/8 of x minus 1/32, the sine of 4x plus c. That is the answer. Okay, so you can see that's a lot of work for one problem. We had to use our trig identities the new ones. We used that one once and this one once in the original, and then we turned around and used this one again to go from degree 4 all the way down to our final answer. Okay, let's do another one that's degree 4. Okay, so example 2, we'll put some limits on this time. So this time we'll have the integral from 0 to pi over 3 sine to the 4th of 3 theta. We'll just change the variable name to sort of have something different with respect to theta. Okay. So you can see there isn't a cosine in there. That means it's cosine to the 0 power, right? So to handle this, we have to use our trig identity that the sine squared of 3 theta would be equal to 1 minus cosine of 6 theta. We have to double that angle all over 2, and we're going to do that twice, right? So this becomes, go ahead and do this. Okay, this will become the integral from 0 to pi over 3. Let's bring the 1/4 out like we did before, and we have to FOIL the numerator of our identity. So we end up with 1 minus double the middle term, 2 cosine of 6 theta minus or plus cosine squared of 6 theta. This time, before I start breaking this up, let me just rewrite. So this is another way to do it. Let's just rewrite the whole thing. So now we have a cosine squared of 6 theta. Let's use the identity again. That's going to be 1 plus cosine of 12 theta over 2. So let's go ahead and put that in for cosine squared of 6 theta. And the whole thing becomes 1/4 the integral from 0 to pi over 3 of 1 minus 2 cosine of 6 theta. And then we'll have an extra factor of 1/2 plus 1/2. Then we'll have, let's see, let me get this right. Oh, times 1 plus cosine of 12 theta. All of that went in. Okay, and I think I have the right number. Oh, one more parentheses there, integrated with respect to theta. All right. Now we may want to break this up now into various pieces and parts and integrate each of them separately. So let's go ahead and do that, but carefully. We'll have 1/4 the integral from 0 to pi over 3 of, let's check them off as we do them. That'll just be d theta minus, we'll have 2/4, so that's 1/2 the integral from 0 to pi over 3 of cosine of 6 theta d theta. You can see this is getting long, so we've taken care of that term. All right, and then if I distribute the 1/2 times 1, and we'll have 1/4 of that, we'll have another, here we go, that'll be plus 1/8 of the integral 0 to pi over 3 of d theta. Okay, and then the last term we'll have plus, let's see, there's 1/2 and 1/4, so that's 1/8 the integral from 0 to pi over 3 of cosine of 12 theta. That is a plus, yes, so That should work with respect to theta. Now it's a mess, but each one of these terms is not that hard to integrate now. So this is just the first term, 1/4 theta from 0 to pi over 3 minus 1/2. The cosine of 6 theta we already saw would be 1/6. And then it would be sine of 6 theta. Evaluate it at 0 and pi over 3 plus 1/8. We're going to have theta again from 0 to pi over 3. If we had expanded, we probably could have condensed these two integrals down. Plus 1/8. And now we have a cosine of 12 theta, so that will be times 1/12 sine of 12 theta using a quick chain. This is why we had reviewed those quick chains a few days back, because if you had to work out the chain rule every time you do one of these problems, they get you can see it's already long. We don't want it to get longer. Okay, so now we have to evaluate. First term is just 1/4 times pi over 3 minus 0, so just 1/4 pi over 3, minus we'll have 1/12. We'll be putting in the sine of 6 times pi over 3, that's sine of 2 pi, which is in fact 0. And then we'll have the sine of 0, which is in fact 0. So that goes away, plus 1/8 times pi over 3 minus 0. We'll just call that pi over 3. Plus, and then we have 1/8 of 1/12. So that's 1/96. And 12 times pi over 3 would be 4 pi. Well, the sine of 4 pi is 0, and the sine of 0 is 0. So all of that works out quite nicely. So the terms that remain, we have a 1/12 pi over 3, or pi over 12. I'm sorry, not 1/12 pi over 3, pi over 12. A 0 term, and then a plus pi over 24. So that looks like it's going to be 3/24. 3 pi over 24, which you hopefully recognize is pi over 8. Whew. So all of that work gives us an answer that is pi over 8. So you can see why these are level 3 problems. When we get up to degree 4, this gets difficult. If we have all even powers and the degree gets even higher, these problems, just the iterations that you have to go through become bigger and bigger. So we won't have you doing any on the homework that go beyond degree 4 by hand. We're going to show you how to use MATLAB or tables to work with those kinds of answers.